In this video, we'll continue our investigation of the solution sets of homogeneous systems by looking at another example. We'll end with a theorem. Okay, so suppose you have been working with a homogeneous linear system, and we're at the last step. We've put the augmented matrix in reduced row echelon form and gotten the following. This is a pivot position. This is a pivot position. The other two rows have been reduced entirely to 0. So x1 and x3 are basic, while x2 and x4 are free. And we write down the equations corresponding to these rows. x1 plus 2x2 plus 5x4 equals 0. From the first row, x3 plus 2x4 equals 0 from the second row. And then the equations we get from the third and the fourth row are both just 0 equals 0. That's useless to us. And we'll take these equations and we'll rewrite them so that the basic variables are by themselves on the left-hand sides of the equalities. x1 equals negative 2x2 minus 5x4. x3 equals negative 2x4. And we've left space for x2 and x4, even though we don't have equations for the free variables. And for each of the free variables, we'll now introduce a trivial equation, because we may not know much about the free variables, but at least we know that they're equal to themselves. we'll now buffer the right-hand side with 0 terms. This process is very similar when we take a system of linear equations and write down the augmented matrix. If a variable doesn't appear in an equation, it causes a 0 to appear in the augmented matrix. So we write in the zeros here. And this can now be expressed as a vector equation. The vector x1, x2, x3, x4 equals, you see we've got these numbers. They're all being multiplied by the same thing, this x2. And if you have a list of numbers that are all being multiplied by the same thing, that's expressible using vectors and scalar multiplication. Similarly, we've got these numbers. They're all being multiplied by the same scalar, x sub 4. So here is the solution set to the system of linear equations that gave us this augmented matrix. We've now seen, between this video and the last video, we've seen 2 examples of the following theorem. If a homogeneous system of linear equations has 3 variables. Let's call them U1, U2, up to UK. Then the solution set of the system has the form U1 W1 plus U2 W2 up to UK WK. where these u's are all running over the set of real numbers. So if we have k free variables, our solutions are the linear combinations of k vectors, one vector for each free variable. Once again, if you have a differential equations background, this is kind of analogous to something you've already seen. Each of the vectors appearing in this linear combination is itself a solution to the homogeneous system. Because remember that these u sub I could be any real numbers. So if we want W1, we just set u sub 1 equal to 1, and all the other u sub I equal to 0. So W sub 1 is a solution to the system. Likewise, W sub 2 is a solution to the system. We get it by setting u sub 2 equal to 1, and all the other u sub I equal to 0. And where I'm going with this, again, for those with a linear algebra background, is that the full set of solutions is a linear combination of linearly independent solutions. We haven't defined linear independence yet, but we will very shortly. So this is just like when you used the superposition principle to take a bunch of simple solutions and add them all up and get a general solution. In this video, we have investigated another example of a homogeneous system of linear equations. We've once again looked at its solution set, and we've stated a theorem for the solution sets of homogeneous linear systems.